Hello and welcome to webinar 6 in this series of 7 webinars on topics of stage construction analysis. Once again, the webinar series breaks down as follows. There were 2 introductory webinars, followed by 4 where I dig into the detail in certain areas, and then finally a summary webinar where I'll try and pick out key points from each of the preceding 6. So in this one, we're moving on to talking about the overall design strategy and the benefits that we get from all of this. So this one also does, to some degree, rely on a level of knowledge from the preceding webinars. So in terms of strategy and benefits, I'm going to talk about 3 things. Going back to talking about the design envelope and eliminating the extremes. We'll talk about simpler wind and seismic drift checking and the potential for reduced second order effects. So starting with the envelope side of things, again, I'm going back to basically repeat something that I started in webinar 1 about why the whole thing is wanted in the first place. So I'll go back to that slide from webinar 1 and just describe how things have been and can be done within TSD. So up until the introduction of stage construction analysis in previous TSD versions, we designed, and I'm talking more about concrete structures here, we designed for a traditional 3D analysis, all the results from a traditional 3D analysis, and we also designed for results from something that we call a chase-down analysis. And this chase-down analysis is our way of emulating the more traditional subframe analysis that engineers have done prior to having the ability really to do 3D analysis on buildings. Now, the concern or complaint, if you like, from some customers using TSD is that this, considering both ends of this envelope, is or can be over conservative, and stage construction analysis can be used to eliminate some what you might regard as unrealistically extreme results from one end of the envelope. So in future, for TSD design, that's what we've enabled. We can stop designing for the 3D analysis, start designing for some stage construction analysis results, and get a little bit more economy. And just to try and put some numbers to this in again a simplified example, and I'm going back to an example that I started in webinar 1, 3-story structure. I've got a transfer beam at the bottom, so as an engineer I'm thinking this beam's big and strong, it holds up this column, and I'm expecting to see a bending moment profile on these beams above where there's hogging at the central support. When I run a traditional 3D analysis, I'm seeing a bending moment diagram in the supporting beam that I would expect, but I'm also seeing, as this beam deflects down, the beams above also deflect, and the amount of deflection at the central support is causing a bending moment that is greater than the effect from the continuous loading on that beam. So you can still see a sort of shape there, but there's as this support sinks, I'm not seeing the bending moment profile that I would expect as a traditional engineer, or I would have expected to be designing for. At the other extreme, I've got our chase-down analysis, where we do see a bending moment diagram, quite small scale here, but we're seeing, instead of seeing a sagging moment of 33, we're seeing a hogging moment of 30 at this central support. So these are the sort of result that a more traditional engineer would expect to be seeing and to be designing for here. I start going again, looking at the numbers in more detail. 3D analysis, I've got a sagging moment in this transfer beam 295. When I start to introduce stage construction analysis, again, as I've talked about in other webinars, you can put different assumptions in here. So this one's stage construction analysis with 4 stages at 4-week intervals, and I've only got a third of the ultimate loading that I will ultimately apply going into the construction stages. And this one's stage construction analysis at a much slower pace of construction, 3 months between stages, and I'm putting 2/3 of the loading into the construction stages, with the balance coming at the ultimate limit state. So this 295 changes to 310, changes to 332, but even at this extreme, it's still not the 411 that we get from the chase down analysis, which an engineer, doing things in the old-fashioned way of designing these beams, getting reactions, chasing them down, and designing this beam for the load that goes on it that way, would have designed it for. So stage construction analysis doesn't necessarily deliver you what you might traditionally want to design for. You might have different opinions about what it's correct to design for here, but I'm showing the extremes. More, perhaps, well, it's a bit subtle, more importantly, the up here in these beams, I've got 3D analysis giving me a hogging moment at this end support of 65. Whereas if I designed that as an isolated 2-span beam with framing into columns at each end, I would only be designing that for about -15. So a lot more moment design there. I'm also designing it for a sagging moment here, where I'd expect to be designed for a hogging moment. So the stage construction analysis, this hogging moment at the support here drops to 61 and to 56, and the sagging moment, the span, also drops to 29 and 25. So you can see some potential economy creeping in the design of these upper beams if you exclude these results and choose to design for one of these values. So where I'm sort of focused in talking about that is how excluding the 3D analysis results and choosing some level of stage construction analysis that will eliminate the extremes at that end. Another question that people could ask is, could the stage construction analysis be used to emulate the sort of expected results you expect in these beams at another level? And in theory, yes, but it's quite difficult to achieve. So actually, you probably need to consider isolated loading on a floor-by-floor basis to achieve something approaching that. So this view here is not even a stage construction analysis, it's just an analysis of that model where I don't load anything except that beam. And then I get an expected moment profile on that beam. I still get moments going to the transfer beam as it sinks to carry that load, but it's a way of getting something more expected. So that you can get these results by, or get something much closer to these results, but you have to start thinking about patterning your load within your 3D analysis, whether that's an unstaged or staged 3D analysis. And so that's why I think we have to still think about designing for this sort of situation that we get from the chase down analysis, or something very close to it. So yeah, you could start to do that, and so creating a much more complicated set of loading conditions to think about. And you could even start to think, look at other what ifs. What if the transfer beam is not cracked while the other beams are, and then it's much stiffer, and then again you force this sort of profile. So there's a lot of what ifs to consider. So traditional 3D analysis or stage construction analysis could be used to produce results away towards this end, perhaps, but it would be a lot of hard work. So in terms of the design envelope, what we recommend is that it's easy to do it this way. If you include stage construction analysis in the design stages, you include stage construction analysis, and then the default is to exclude the 3D building analysis. So you've got that range of results being considered, and it's just the easy way to do it. If you wanted to try and do things a different way, you've got the options to check things on and off here. You could do it. I would just say be be sure you understand what you're doing and what the implications of it are as you head down that road. So now move on to the simpler wind and seismic drift checking. So stage construction analysis always tends to be raised in the context of taller buildings, and those sorts of buildings are obviously more susceptible to significant second order effects and significant wind drift concerns. And these two things have conflicting requirements. So in a 3D building analysis, you've got a single analysis model for all the cases and the combinations. And the stiffness modifiers that you apply to that have to be appropriate for, or can only be appropriate for, one of those things at one time. So the safer thing to do is to make them appropriate for the second order analysis, which means that you will overestimate the drifts using the drift checks, which should be based, the adjustments there should be based on what I've talked about as a transient loading level. Talked about that, I think, in webinar 4. So what that means, what we've seen some proportion of engineers do, is that they start to maintain a separate copy of the model. So they've got one copy of the model for the design, and then a separate copy of the model where they use adjusted stiffness modifiers specifically for the drift checks. Maintaining that, establishing that, it takes a little time, but the maintaining that, if you're working through the evolution of a design, then constantly changing two models or constantly having to re-establish one model from the second model from the first becomes time consuming and potentially a little error prone. So the way you can do this with stage construction analysis, and what we need to remember here is that stage construction analysis doesn't produce any load case results. So again, as I've described in previous webinar, the load is elevated through the construction stages to get to the end of construction, and then you elevate it again up to design loading levels. And you can't readily go back down to only a load case by load case level, or it can start to do strange things if you do that sort of thing. So the drift checks are based on the results from load cases. Those don't come from a stage construction analysis. But alongside doing the stage construction analysis, we continue to do the 3D building analysis in the unstaged version of it. And so we can still use the results from that specifically for the drift checks. And all you have to do is set the 3D building analysis stiffness modifiers, because you're now not relying on the 3D analysis for design. You can set them to the values that you feel are appropriate for the drift checks. Now, I'm probably making this sound complicated, but we have picked it up in the help system again. If you need more guidance on it, it is a relatively simple process. You start to use stage construction analysis. You are now not dependent on those modifiers, so you can change them, talk about what you might change them to. And another note here is that if your only concern, because I say many people have raised this with us about getting drift checks done for service load stiffness adjustment factors that are more appropriate for transient loading, then you can still use the stage construction analysis, but in effect switch it off by if you set the load in the construction stages to 0, then as I've shown in other webinars, then effectively the stage construction analysis just becomes, if you like, a long-winded way of doing a first-order linear analysis, but you do get this benefit of having different stiffness modifiers applied to the different different combinations in the different design stage categories. If you were to go down that road, you could even edit the stages so that the entire model is in a single stage. So it just comes into existence with no load on it, and then the load's applied. And then the final part in here about the benefits is a potential for reduced second order effects. So again, stage construction analysis tends to be raised as a requirement for the taller buildings, and again, these buildings are more susceptible to, or more likely to be susceptible to significant second order effects. So second order effects, the amplification of analysis results is influenced by the stiffness. And as you increase the stiffness, you reduce the deflection, and therefore you reduce the second order effects. So again, webinar 4, we explained about how the combinations in the different design stages have different stiffness modifiers. And combinations involving wind or seismic loading will typically have smaller stiffness reduction, i.e. they will be stiffer and therefore have reduced second order effects. So if your design is being, if the design of your lateral load resisting system is being controlled by wind or seismic, there is this small potential for a more economic design. Now, I tried to create an example that would show this. It did actually take a few goes at it, because I think the benefits are there, but they're not likely to be hugely significant. So I've got here a 50-meter tall building with flat slabs and a core where I've got a C-shaped core wall, another wall panel over on the right, sorry, it's a little bit difficult to see, and then some coupling beams that connect the C-shaped core from the outlying panel to the outlying panel. And then I've designed this for stage construction analysis and the chase downs for a typical set of gravity and wind combinations. And I've set it so that the reinforcement is automatically selected. It's designed for second order analysis. And I've got to the point where everything's passing after an auto design. So what I can then do is switch it into a check design mode and switch off the stage construction analysis. So I'm now designing it for the 3D analysis results. And when I check it that way, I get 3 wall panels and 4 beams that fail. So these are the wall panels and beams where the traditional method has got some level of over design. So let's start to look at the results for the beams first of all. And I'm looking at results for the coupling beams. There's a wall panel here. So the coupling beam going between the wall panel and the plane of the beam, and then it's attached to another wall panel which is out of the plane of the beam here. And you can see the bending moments in the beam for one of the it's actually the critical load combination in this situation. And I've got showing the results here from a first order linear analysis. I've got 1743 kilonewton meters at the end of the beam here. In the second, when I run a second order analysis, that value goes up to 2212, so that's nearly around a 20% increase. And when I run the second order linear stage construction analysis, where it's got these different stiffness adjustment factors for this combination, which includes wind, then that comes back down to 1958. So instead of getting a 20% increase, I'm getting something more like a 10% increase in bending moment in the stage construction analysis. And in fact, if you look around the model or looked at those numbers, you can actually see that the forces are changing in every single beam. It's just that there are only 4 where the change is significant enough to swap it from a pass to a fail status when you start to consider the 3D analysis results. So there's potential everywhere, and it's just a matter of where you cross the line. So showing it that way, I'll come on to that in a second. I just start, first of all, say it's a similar story for the wall panels. It's a different load combination that controls the panels that fail. And in fact, it's a combination where the panels in that at the bottom of the core, as it's going over, you're getting a tension and push-pull effect and tension compression effect at the base of the core. And the panels that are failing are in tension, and that tension is amplified by the second order analysis, and so it's not amplified as much in a stage construction analysis, second order analysis. So tension level drops, and the beam that passes for stage construction analysis, not the beam, the wall that passes for stage construction analysis then fails for the when you consider the basic second order analysis. So as I say, looking at we're only looking at pass fails here, so it's things are changing in all of the members. It's just that you're just crossing a threshold when you look at the pass fail. If I look at utilizations, it might give a better feel for the level of change. I'm focusing just on the wall panels, then the average UR is 0.71 when I designed for the stage construction analysis and the chase downs, and then when I check it, for the second order analysis, then the average utilization ratio goes up to 0.72. So for this model, on average, there's only a kind of a 1% change in what part in the 1% potential for benefit on average. So on average, it is probably quite a small benefit, but it is a benefit, and it's a benefit for your customers, and it's potentially a benefit for the environment too, as we design a more efficient structure. And a final note while I'm working with this model, I'm constantly talking about how I've got traditional 3D analysis at one end of the range, chase downs at the other, and that stage construction analysis is capable of producing results that are input dependent that lie somewhere in this range. For this particular model, if I design it for the building analysis and the chase downs and then check it for the stage construction analysis, everything still passes. So for this model, that's proving that this is the case, that everything lies within the range. I can't say that this is absolutely guaranteed. I think the principle of this is right, but when we're playing around with these stiffness modifiers, and as you move them from into the different categories, the ratio of modifier used for columns and walls that's coming from the ACI code moves around a little bit. So that will throw things around in a slightly different way. So it is just possible that you could find something that goes the other way, but I think that's a very unusual sort of case, and it's it would be a reasonable result anyway, in that you're using the recommended modifiers. So in overall summary on this section, I'm talking about benefits primarily. For the design envelope, the benefit is that you can eliminate extremes, and again, the benefit is the potential for more economic design. For the wind and seismic drift checking, the benefit is for you as designers, where you can make the process more efficient, and if you're not maintaining multiple models. And then for the reduced second order effects, again, the benefit is for a potentially slightly more economic design. So that brings me to the end of webinar 6 on design strategy and benefits. Thank you.